Hello everyone. So this is a question from NEET 2026. Match list 1 with list 2. In list 1 we have certain complexes, and in list 2 we have the type of isomerism that they show. Okay. So the chapters involved is coordination compounds. Okay. So we know that two or more substances having the same molecular formula but different structural or spatial arrangements are called isomers. We know that. Okay. And coordination compounds show two main types of isomerism, very important. Coordination compounds, they show isomerism, and the two main types of isomerism that they show is A is structural isomerism, and B is stereoisomerism. Okay, so structural isomerism arises due to difference in structures of the coordination compound. Okay, very important. So it arises due to difference in structures of coordination compound. Okay, so the structure itself is different in structural isomers. Okay, so we'll talk about stereoisomerism in a while. So there are four different types of structural isomerism. So those four types are: first one is ionization, second one is known as solvate or hydrate, third one is linkage, and fourth one is coordination. Okay, so let's discuss about solvate or hydrate and linkage in detail since they are present in list 2. Okay, so these two guys are important. So let's talk about solvate or hydrate isomerism first. So compounds which have the same composition, obviously, but differ in number of solvent molecules present as ligands in the coordination sphere and as free solvent molecules present outside the coordination sphere. Okay, very important. So I will write down this. Obviously, they have the same composition, or you can say the same formula, but differ in number of solvent molecules present as ligands in the coordination sphere and as free solvent molecules present outside the coordination sphere. Okay, so in them, the solvent molecules present as ligands in the coordination sphere and as free solvent molecules present outside is different. Okay, so we'll see that using examples. And if the solvent that we have mentioned in the formula, if we use the solvent as water, then it is known as hydrate. So if the solvent is water, then it is known as hydrate isomerism also. To understand this, let's take an example. So let's talk about option D. Okay, option D, they have given us the complexes CrH2O6 and Cl3 outside the coordination sphere. So this is your coordination sphere. Okay, so how many water molecules are there inside the coordination sphere? 6. And how many are outside? 0. Okay, so this guy also exists as in the form of isomers. So the other two forms are CrH2O5 5 Cl Cl dot Cl2 dot H2O, and it also exists as Cr H2O 4 Cl2 Cl dot 2H2, right? So can you see all these three guys have the same composition or the same formula, but the number of water molecules or solvent which are present as ligands in the coordination sphere and outside the coordination sphere is different. Here you have 6 inside the coordination sphere, and here you have 0 outside the coordination sphere. Here you have 5 inside the coordination sphere, but 1 present as free solvent. Similarly, here you have 4 inside the coordination sphere and 2 present as free solvent. So therefore, option D, or we can say that 2, that is solvate isomerism, is matched to D, and D, the complex is CrH2O 6 Cl3. That is, this complex shows solvate isomerism. Okay. Then we have to talk about linkage isomerism. Hmm. So this type of isomerism occurs in compounds containing ambidentate ligands. Very important. So this type occurs in compounds containing ambidentate ligands. Okay. So what are ambidentate ligands? So when more than one atom in a unidentate ligand function as a donor, then it is known as an ambidentate ligand. Okay, very important. So when more than one atom in a unidentate ligand function as a donor, then that ligand is known as ambidentate ligand. Okay, by unidentate ligand, obviously it can donate maximum one electron pair to the central metal atom. Okay, so when you have a unidentate ligand and when you have more than one atom which can function as a donor, then it is known as an ambidentate ligand. Okay, for example, NO2 minus. In NO2 minus, either N or O atom may act as a donor, giving two different isomers. Okay, for example, let's look at option C. So option C, the complex is CO, NH3, 5NO2 and Cl2 outside. So it has N acting as the donor atom. So here N is the donor atom. Okay, so you can also represent it in this fashion, that is NO2 minus is the ligand and N is donating electrons to the central metal atom cobalt. Okay, this guy can also exist as CO, NH3, 5, ONO and Cl2 outside. And in this case, an O atom is acting as the donor atom. So this guy is donating electrons to the cobalt this time. So you can also represent it in this fashion. So ONO minus. So oxygen is donating electrons to the central metal atom now. So therefore, fourth, that is, linkage isomerism is matched to C, and the complex is CO, NH3, 5, NO2, Cl2. So therefore, we can say that this particular complex show linkage isomerism. Okay. Then we have to talk about stereoisomerism, which arises due to different positions and arrangement of ligands in space around the metal ion. Okay. So stereoisomerism, that is the second type of isomerism shown by coordination compounds, arise due to different position and arrangement of ligands in space around the metal ion. Okay, so that's why stereoisomerism is also known as space isomerism. So here the position of, or the arrangement of ligands in space is going to be different. Okay, so it is of two types. First one is geometrical. Okay, so geometrical occurs in heteroleptic complexes. Important. Geometrical isomerism occurs in heteroleptic complexes due to different possible geometric arrangement of ligands. Okay, so before we understand this definition, this word is very important: heteroleptic complexes. So by heteroleptic complexes, I mean those complexes where the central atom or ion is bonded to more than one kind of ligand. Okay, the central metal atom is bonded to more than one kind. That means there should be different kind of ligands. Okay, for example, in option A we have this guy, pt nh3 whole twice Cl2. So this can exist as either as pt Cl Cl nh3 nh3, or it can also exist in this form, pt Cl Cl nh3 nh3, right? So obviously this guy is a heteroleptic complex, and that's why it will show geometrical isomerism, because there are two different geometric arrangement of ligands. This is known as our you know um, cis isomer, because similar groups are present on adjacent position. They are on adjacent positions, and this guy is our trans isomer, because similar groups are present on opposite positions. You can see chlorine and chlorine opposite, NH3 and NH3 are present in opposite positions. So therefore third, that is geometrical isomerism, is matched to A. The complex is pt nh3 twice Cl2, or we can say that this particular complex show geometrical isomerism. Okay, and the second category of stereoisomerism is optical isomerism. Okay, and optical isomers, we know from organic that they rotate the plane of polarized light in opposite directions. One will rotate it towards right, which is known as dextrorotatory. One will rotate it towards left, which is known as levorotatory, right? And the two isomers are non-superimposable mirror images of each other. That's also we know, right? The two optical isomers are non-superimposable mirror images of each other. Okay, and optical isomerism is common in octahedral complex. Very important, octahedral complex. Obviously they will have coordination number 6, and so they are common in octahedral complexes with coordination number 6, and also involving 1, 2 or 3 symmetrical dientate ligands. That's how we recognize if someone can show optical isomerism or not. So this is very, very common in octahedral complexes with coordination number 6 and having or involving 1, 2 or 3 symmetrical dientate ligands. Symmetrical is it is containing a plane of symmetry. Didentate is, a ligand attached to central atom by two coordinate bonds. Okay, and so we'll see an example in option B, that is this guy COEN 3 3 plus. It is an octahedral complex. Check. Okay, and also coordination number is 6, and it contains three symmetrical didentate ligand. That is this guy. Okay, and this EN is an abbreviation for ethylene diamine, right? We know that ethylene diamine, which is basically NH2, CH2, CH2, NH2, right? So therefore, it is a didentate ligand because there are two simultaneous donations from the same ligand to the central metal atom. Okay, and also it is symmetrical. So therefore, it satisfies the condition, that is octahedral complex. Yes, coordination number 6. Yes, because one didentate ligand can form two bonds, so 3 can form 3 into 2, 6. So therefore, the coordination number is 6, and also it contains three symmetrical didentate ligand. So therefore, it can show optical isomerism, and this guy exists in two forms. Okay, so since it is octahedral, so 1, 2, 3, 4, 5, 6. En, because it is didentate. En, En. You can place it in front of a mirror to get its other isomer. So the other one will have obviously octahedral mirror image. En here, En here, and En here. So you can say this is the dextroform, although that should be determined experimentally depending upon which direction they are rotating the plane polarized light. Let's say this is the LEVO one, so it is the symbol L. So therefore, um, we can say that first, that is optical, is matched to B, the complex COEN 3 plus, or we can say that this particular complex can show optical isomerism. So therefore, the final answer is going to be, so PTNH3 twice Cl2 will show geometrical. COEN 3 plus is going to show optical. CONH35NO2 Cl2 is going to show linkage, and CrH2O6 Cl3 is going to show solvate or hydrate. Okay, so this is the final answer. Okay, thank you.